Hi there, I'm Andrew Bunnell, and today let's take a quick look at the Ampere law experiment. So let me go ahead and fade over to my second screen. Ampere's law is the closed path integral of the B parallel times dl is equal to mu naught I through. And if you've read through the discussion, you're just going to see that we're going to convert this into a summation. So we're going to do a Reimann Sum today, and also to convert the B parallel dl to a delta L, we're going to be doing a dot product. And if a summation and a dot product sound a little scary, well, let's say they're not that bad. And that part's maybe the easy part today. But there are lots of pieces of information of this experiment that we got to keep track of. And so that's the challenging part. And the error analysis isn't that bad either. We kind of walk you through how to do a complicated error analysis when we're doing a summation or an integral with numerical data. All right, so right above me, I also have the applet in the data table. Usually when it opens up, it's right on top. Now this applet shows a vector field, and we're going to be stepping this point through a path on the vector field. And as we do that, it's going to be recording the change in location. So there's an Lx and an Ly. Don't get confused with this lowercase l. This is the path distance, not the current. The current will be read right here on the applet. Then also at each of those points, we're going to record the magnetic field component at each of those steps. So let's go ahead and click play and watch this magnetic field generate. Now if you notice on this, I can hold down the left mouse cursor and drag it around so you can get a better view for the post lab. The post lab, you're going to take a snip of this and write a figure caption and then give some of your results. Also really quick, there is this little Z slice, and if you're unable to position this thing really well, here's kind of what that step is. And do you notice how the Z arrows point up and then the Z arrows point down at that location? All right, let's go ahead and hit reset and go ahead and click play again. As this thing forms, it recalculates and recalculates the magnetic field at every single point on this plane. And it's done. Now the next thing we're going to do is we're just going to step this dot through, and as we do, once again it's recording the change in X and the change in Y. So we're doing steps about 7.5 centimeters, or sorry, 7.5 millimeters. Step, 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 all the way through. And then we have a spot where there's 0 on the X, and then there's a spot where there's 0 on the Y. And after that, you won't get any more changes, but the current will keep changing as it has taken another step. And as you click through here, you'll notice the current has a little bit of deviation, and that's similar to a real meter. And so we're going to find the standard deviation of that in a little bit as part of our uncertainty. But I'm going to go ahead and Control-A, Control-C, copy this data and paste it into an Excel workbook. And today we're not going to use the fitting worksheet, but make sure you type your name in there. Now I already have 2 sets of data, but I'm going to go ahead and walk you through how to do it again. And so I'm going to go ahead and right-click, paste, and I just pasted that data right there. I'm going to go ahead and delete this formula and show you the next step. So the next step, let me delete all these formulas over there too. I'll keep my current measurements. Okay, great. Now the next step is we got to calculate the left side and the right side of equation 5. Equation 5 is Ampere's law in the numerical form where there are, let me just pull it up here on the screen, where there's also a number of turns. And so our loop has 5 turns for this one, and so we're going to keep track of that as well. Okay, so I pasted my data, and we got to calculate the left side. The left side is simply the sum of the dot product, and the dot product is the step in the step in X multiplied by the magnetic field in X, plus the step in Y times the magnetic field in Y. And if there was a step in Z, we would also do plus the step in Z multiplied by the magnetic field in Z. So let's just go ahead and do that. Equals the step in x times the magnetic field in x plus the step in y times the magnetic field in y equals, and copy it down the column. Now, the left side is really the sum of these little steps. And so what we're going to do over here is first off label a cell beyond in column M or beyond. Label it left side equation 5. And we're going to equal the sum. Oops, not the one. Oh, I did it again. The sum. And I'm going to select this and shift end down and select the whole column. So there we go. We get a 1.25 times 10 to the negative 4 Tesla meters. Tesla meters. How many meters can a Tesla drive? No, I'm just kidding. Okay, now for the right side, we're going to calculate mu naught n and I, mu naught times n times I, and mu naught is 4 times pi. And you need those parentheses. I am just typoing like crazy. Pi, and then parentheses, and then times 10 raised to the power of negative 7. And I forgot to put an equals out in front. Okay, so we get 1.26 and some change, and I can decrease the digits a little bit. Okay, now the number of turns is simply 5. There's no uncertainty, and there's no uncertainty on mu naught either. It's a fixed constant. Now for current, there's going to be uncertainty, but for a placeholder, what we're going to do is we're going to go to the applet, and we're going to record a number of what the current read. So I see 20.02. And we're going to come back into this formula later and edit it to find the average later. Okay, so this is just simply equal to mu naught times the number of turns times the current. Now there's one more problem right here, and that is I didn't consider the direction of the current. And so I'm not going to give you the answer on the direction of the current. I want you to look at the graph and look at how that little dot steps around the path. And I'm just going to tell you, though, it is negative, but you got to answer why it has to be negative. And when I do that, I get a number that actually looks to be the same number as up above. And so I got really lucky. Well, not exactly the same. They're pretty close. But how close are they? Well, we got to calculate uncertainty. And so to calculate uncertainty on the left side is a little bit trickier. On the right side, we're going to need the current and the average. Well, we're going to need the average current and the standard deviation, or actually the standard error of the current, really. And so to do that, you go back to the applet, and you click step, and the current number change, and you click step, and the current number change, and you need 6 measurements. And I already have 6 measurements right here. And I'm just going to type in average and highlight those current measurements and hit enter. And I can decrease the digit right here some. And then I need the standard deviation, stdev, of those same 6 numbers. And then for the standard error, it's the standard deviation divided by the square root of the count. And I have 6 measurements, so the square root of 6. And now I can actually highlight all 3 of those and decrease the digit to a rule 1 and 2. Now the standard deviation needs to take off 1 more digit. Review Appendix A if you've forgotten how to round digits. Okay, so now that I have the uncertainty and the standard error, I can go to the right side of equation 5, and I can go equals times. Now typically we do a square root, and so I'm going to go ahead and do that. And we think through our formula, and we only have those 3 things. Those 3 things right there in the formula. And so we'd have the ratio of the uncertainty of this over that, the ratio of the uncertainty of that, and the ratio there. However, there's only the uncertainty there. And so when we square that, it deletes the square root. And so we can just simply times it by the ratio of our measurement divided by the standard error. And actually, right here, we can take it by the ratio of, actually, I have those backwards, oops, by the standard error divided by the average measurement. Okay, great. Now we also need to include what are uncertain, let me see, we needed to change it down here from the N6 down to the average N value. We need to go back in and change that value now that we have the average. Okay, there we go. Now, Now that number and that number don't match, and so let's go ahead and click on Format Paint and do all 4 of them and decrease the digits a little bit. And we actually should go probably to there. This might be an easier way, and then what you'd do is you'd write it in standard notation, either 1257.4 plus or minus 0.8 Tesla meters, or you could type it in, you could actually write it this way as well. It's a little bit harder to read this way. Now, to do the uncertainty for the left side of equation 5 is a little trickier because we're doing a summation, which is an integral of all these rows, all these discrete delta L's. We need to find a little bit more information. The first thing we need to find is the B parallel. And to find the B parallel, we're going to do a conditional statement. So we're going to say if this number is 0, is equal to 0, then make it this number. And if it's not that number, then make it this number. And so I type it in, and you notice that this number matches that number with an extra digit. And now I copy that formula down the column. Now the next thing is the step size. And you could just say it's the ABS of this one plus this one, but remember, these are actual components. And so what we really need to do is do this one squared plus this one squared. Yes, this one's a 0, but remember the Pythagorean theorem to get the magnitude. So we're going to do equals the square root of this number quantity squared plus this number quantity squared. And now we're going to copy that number down the column. And if we notice, all these values are different, and all these values are a little bit different. So what do we do next? Well, it says in the book that we can assume that the error in the B field reads like a device, and there's a certain limit, and that's 0.0000, 4 zeros and a 5, or 50 microtesla. And that it just reads to that last digit, and there's a little bit of uncertainty there. Now the error in the step size, we can take the standard deviation equals STDEV of that last column that we made. Great. Now we have our 2 uncertainties. We can calculate what the uncertainty is, and that's in meters. We can calculate what the uncertainty is all the way down along this column. And to do that, we're going to do equals sorry, I had to pause it there for a minute to remember. I remembered what the formula was, but I had to remember why. Okay, so the value of the uncertainty right here is similar to what we've done in the past. It's going to be equals to this cell, and then we take the ratio squared, so the uncertainty down here divided by that value, plus the ratio of the uncertainty down here divided by that value, quantity squared. And then we're going to get a whole list of uncertainties that are going to be slightly different than each other. So let's just go ahead and do that. Equals, and we can select that cell. Oops. There we go. Times it by the square root of, let's put in our parenthesis trick first, squared plus set of parentheses, quantity squared, close off the bracket. And now let's go in this first one, and we're going to click on the error of the uncertainty divided by this value. Now we need to fix this one right here, so I'm going to press the F4 button, but if you don't have an F4, you can just type in $signs before the N and before whatever cell you put it into. And then we're going to do the same thing down here, and so we're going to click that cell and hit F4 divided by this cell right here. And the value is 3.7 to the, and it kind of changes back and forth. Some of them are negative and some are positive because we're stepping in negative and positive directions. Now technically it would be all positive, but to calculate the uncertainties, we're going to have to sum up the squares. So once again, we have a whole list of values that we're summing up, and so they each have an uncertainty. Well, just to fix it, I'm going to do is I'm going to just type in ABS, because typically we wouldn't write a negative uncertainty. And now I'm going to copy that down. And if we added a couple more digits to our numbers, we could see that they fluctuate up and down a little bit. So in the next column, we're going to square each of those values, and then we're going to sum them up and then take the square root. So that's equal to this one, quantity squared. Now let's copy that down, and yeah, 10 to the 13th is a really small number, or 1 to the 13th is a really small number, but that's okay. Equals the square root, SQRT, of the sum of this column. And then double parenthesis to close it off. And there we go. Now this number right here, we can decrease it a little bit by one step, or we could write all of them with the same digits. We could say like 1249 plus and minus 0.25, or that would be 2.5 times 10 to the negative 6, it looks like. All right, there we go. And this one is also in Tesla meters. Now to do a z-score, because both of them have uncertainties again, we have to do our slightly more complicated formula. So let's call this one z. Z, and then step over here is equal to SQRT, no, ABS. ABS, sorry about that. This one minus this one, divided by the square root of this uncertainty quantity squared plus this uncertainty quantity squared. And I get a pretty good z-score of 0.32. All right, so you'd name the first one Ampere through, and then you would make a copy of it and name the second one Ampere around. But because I already have those two sheets, I'm just going to go ahead and move and copy, create a copy. And now I have the same sheets, and I'm going to change the applet ever so slightly and then walk it around again. Here we go. I'm going to go ahead and hit reset. And for my number of coils this time, it says between 2 and 9, I believe. I'm going to go ahead and choose 4, and I'm going to go ahead and hit, oh, I got to go back to 4 again. And I'm going to go ahead and hit play. And I'm going to wait for it to finish doing its 4 coils. And now I'm just going to, oh, I forgot one thing. I forgot to change that. I'm going to have to reset it and change it back to 4. And I'm going to change the NRX to 22. I forgot to mention this earlier, but we needed it a box. You can change these things to make the box different, but we really only need to change this one box. Okay, now I click on play, and it's going to curve, and now I have a box that's around this coil. Great, now I can step really quickly through. Now, just to let you know, in the hands-on experiment, walking this little mouse, a physical little mouse, which is a Hall probe around this coil, is one of the most difficult things to do. It takes a long time to take this data. So I'm going to come over here to my data table, Control A, Control C. So you can be glad that you can get through that data table really quick. And I'm just going to paste it in, and I'm going to scroll to the bottom. And uh-oh, look at this. I have more data here than I have here. Well, this is pretty easy to fix. I can just highlight this whole bottom row and double click on the bottom corner. There we go, we fixed it. Now we have to come up here and double check a lot of our formulas. And I click on this formula right here, and it has 46. And I scroll down to row 46, and I have more data after that. So I scroll really down here, and I need the formulas to go all the way to 62. So when I click on that, I see that there's a formula of 62 in the formula, J62. And so I need to click through all my formulas, and anywhere there's a 46, I need to change it to a 62. So there's a 46 there. There's another 46, 62. And there's no 62 there, or there, or there, or there, or there. There's no 62 there. There's not one there, but there is one there. Okay. Now there's one more thing, and that is, it says, for this loop, make the uncertainty 0. All right, when I make the uncertainty 0, this value right here, if I drew from that cell, would have changed to 0. So I'm going to hit escape, and I'm going to make this average right here 0. Okay. Now this z-score says you can't divide by 0. And yet my number right here actually came out really good this time. I'm 0 within, I actually am 0 within that. And right here I can't divide by 0, and so I got to change my formula a little bit because of, we're only comparing now this number to this value with 0. and I have a z-score of 0.02. So this time I got lucky and took some really careful data. And that's about it for today. Thanks for watching.